Todos que nos assistem agora diretamente pelo YouTube, nesse novo seminário da série de seminários do INCT e Coniote. Para quem não sabe, o INCT é um Instituto Nacional de Ciência e Tecnologia, promovido pelo CNPq, é um grande projeto que reúne várias instituições. No nosso caso, são mais de 20 universidades, mais de 100 pesquisadores, muitos alunos e pesquisadores pós-doc. E o INCT e Coniote é sobre redes de comunicação e internet das coisas inteligentes. Então, nessa nossa série de seminários, nós temos seminários apresentados pelos pesquisadores do INCT e temos também seminários apresentados por pesquisadores internacionais. Hoje nós temos aqui um pesquisador da Itália, que eu vou apresentar logo em seguida, e por esse motivo a apresentação agora, a partir de agora, vai ser em inglês. So, good afternoon, everyone. We have the pleasure to have here today Professor Andrea Sabbioni from the University of Bologna, Department of Computer Science and Engineering. And his talk will be about models to support Society 5.0 development. Okay. I'm a junior researcher in the Department of Computer Science of the University of Bologna. And his PhD research was about infrastructures to support high quality modern service environments for smart tourism and BCD applications. He also holds a BSc and MSc degree both from the University of Bologna, and his current research interests oriented infrastructures, smart tourism, and B2C digital ecosystems with a strong foundation in information processing systems. So, Andrea, thank you very much for agreeing to give this keynote anytime you want. Okay, thank you again.
So, good evening, everybody, and thank you, Carlos, for the presentation. And I would like to thank also Nesso for inviting me to contribute to this project. Today, we will start with exploring what is Society 5.0 and especially why we need this new concept. Then we will see how Cloud Continuum can actually support the development of next generation society or Society 5.0. We'll then explore in particular two topics that we are experiencing and we are researching during this day, which is platform engineering and serverless computing, that we believe can actually support in a better way the development of a smarter society. But let's start with some topics that I think are very familiar to the project. And in particular, we saw that in the last year, new technologies such as artificial intelligence, pervasive IoT, next generation networks, and in general, all the new technology has given access to an incredible amount of data and new technologies that enables us to extract new values in many sectors in our everyday life. In particular, if you want to make an example, let's start with a very common and pervasive example that is the one of smart city. In the case of smart city, the new artificial intelligence techniques like the pervasive IoT, but also the cloud and edge computing infrastructure has enabled to process the data that are gathered all across our cities and enable a better decision making by companies, transportation, and also the city government. But nowadays, while we are exploring smart city, we are facing also a very complex use case. And in particular, this is because when we are thinking about smart city, we need also to think to all the impacted areas by the smart cities, such as transportation, energy, public services, environment, but we can also think to smart health, smart agriculture. All these areas are in a way or the other connected with smart cities and are impacted by the evolution of smart city. But let's make another example. Let's take the example of smart tourism. Even in this case, we have a very complex use case in which the evolution of new technologies has enabled to live the tourism and to enjoy new way of making tourism all across the world. But again, we need to consider many sectors that integrate with the tourism. If we think to smart city, it has to be connected with smart tourism, as well as smart transportation is deeply connected with smart tourism. But as well, there are many types of tourism that can interconnect with other societal areas, such as tourism that is bound and is strongly coupled with, as an example, health, tourism that is bound with businesses, and so on. But let's take a far remote use case. Let's consider the evolution that we are facing now when we are shifting our domain areas of Industry 4.0 to Industry 5.0. And in particular, we are seeing that Industry 5.0 is seeking for a more human-centric, sustainable. To do this, especially in Europe, the European Union has said that one of the key factors is a deep integration with the territory. And so again, we see, even in a strange area that was mostly innovated by its own, we are seeing many connections with smart cities, again, smart transportation, the everyday citizen life, the smart grids that can give powers to our factories, and so on. So here we arrive to the concept of Society 5.0. Society 5.0 see a human-centered vision that wants to integrate all the new technologies to create a more sustainable, inclusive, and innovative society. And to this, so we want to, or in general, Society 5.0 wants to overcome the innovation that, as far as now, it was sealed. So it wants to foster the fact that all this domain have to evolve and create the technology and create a program of evolution together. And in particular, to do so, the Society 5.0 is a concept that has been initially proposed by the Japan government to highlight this necessity of making integration, of understanding what is the evolution of different societal aspects all together. And to do so, we want to have an holistic transformation of all our aspects while integrating all the new technologies that we are seeing. But while we are speaking about this evolution, we need also to think about what can enable this type of evolution. And one of the technology that has, at least in my opinion, supported most the evolution of our society is cloud computing. As a matter of fact, cloud computing that enables the convenient access to resources and new technology across the network, I want to focus on this particular word, that is convenient. As a matter of fact, cloud computing has enabled the access to a convenient access to many new technologies, even to small and medium, as well as large business enterprises. And at the same time, it has enabled researchers to experiment with these new technologies. And again, the word convenient, it doesn't mean only that it's more affordable, but it's also a matter of time. If we need every time to configure and manage all the infrastructure, all the technologies behind, need to know all the protocols and all the technologies to actually access a single technology, it becomes not so convenient in terms also of time. And to support the evolution of different societal sectors, cloud computing has changed a lot of the time, trying to adapt to the different needs of different societal aspects. And in this evolution, we saw cloud computing adapting with different models of ownership, switching between mostly public cloud services accessible by all the person through a payment method, to also different type of ownership like private or federated. But more recently, since many sectors are seeking the need for a more decentralized access to resources to achieve better latency, or better resiliency of the infrastructure, we are seeing also new model of distribution of cloud resources. And so we are shifting from single cloud infrastructure to multi-cloud and cloud edge infrastructure. At the same time, we have shown a differentiation in the model of services of cloud computing, passing from classical infrastructure as a service, where the user has full control of all the infrastructure and all the configuration of the infrastructure, to more vertical specialization, like backend as a service, database as a service, that enables to access to a very specific, well-maintained and well-configured service in like no time. But then all this innovation, all this adaptability has also started to seek it to have hybrid models. And then cloud computing is evolving toward what we are calling now cloud continuum. And in particular, when we are speaking about cloud continuum, we refer about a methodology, a series of technologies, an organization that can exploit various deployment models, various location models, and various service models of cloud computing, all at the same time. And this can be scaled or adapted dynamically over time. And this is all done to support the different use case and the needs of the different use case, while we are leveraging a very distributed and heterogeneous infrastructure. But with these complexities, many challenges emerge, and these challenges are risks to make the cloud continuum less convenient in particular. And in particular, we are facing, as we said, a more complex multi-cloud, a very hybrid environment in which we have to deal with many protocols, many technology, very heterogeneous hardware, very different interfaces. And then we are facing also, for this reason, a huge talent and skill gap. As a matter of fact, it's very hard to find a single person or a group of persons that at the same time can handle the business logic, the complex infrastructure that we are facing with Cloud Continuum, and make operate everything together. And on top of that, we have also to consider classical distributed system challenges, in which we need to decide if we want our system to be all consistent, to be resilient, to be almost available, and so on. So we will see today three main approaches, and in particular the limitation of these approaches, that can actually help to tackle the complexities of a cloud continuum. We will start with what is the state of the art, especially for business, which is DevOps, and in particular an integrated and agile methodology for building cloud continuum application. We will then switch to new and, let me say, more new and more innovative methods that are platform engineering and serverless computing, that by trying to hiding part of the complexity of the infrastructure and at the same time trying to expose high-level interfaces, aims to support the adoption of a cloud continuum infrastructure. But let's start with the most simple one. As almost as we know and we have experienced in the past 10 years, DevOps is a set of practices and tools that has helped us to automate the repetitive tasks, especially in software and infrastructure lifecycle. It's nowadays the most widespread approach for Cloud Continuum, but let's see why. Because by design, the Cloud Continuum DevOps already offers some tools that enables us to tackle the major complexities of Cloud Continuum. And in particular, if we think about the technicalities and as an example, infrastructure as code. Infrastructure as code actually enables us to define through code what we desire as infrastructure. And this makes the entire infrastructure very easy to reproduce. And this is a key important factor, obviously, for Cloud Continuum environment and to enable the development across multiple business and teams. Then we have templating, and with templating, we can actually abstract some of the complexity of Cloud Continuum by enabling some sort of automation, some sort of modularization of code and configuration that actually simplify the configuration of Cloud Continuum architecture. Finally, we also know that we have CI/CD and continuous integration tools that actually enable us to automate repetitive tasks across Cloud Continuum. But when we consider Cloud Continuum DevOps, we face many limitations. The first thing is that we cannot have active logic of assurance and control. In particular, while we are configuring all our infrastructure cannot actually react to changes. It's very slow to react to changes. And every time we need to interrogate or involve a team to make changes. This makes a huge challenge in the case of Cloud Continuum, as we are continuously facing changes, failures, or change, as an example, in the number of users that are consuming services on top of our infrastructure. Also, the huge heterogeneity and complexities of a Cloud Continuum infrastructure limits increase the learning curve to all the tools that we need to master for manage a Cloud Continuum infrastructure, but also we are facing today a lot of heterogeneity also in the tool for Cloud Continuum. And this creates, again, a higher learning curve because a single developer has to face the complexity of the business case and at the same time, the complexity of managing many different tools to face the complexities of the infrastructure. So we are here, here I propose a new approach that is starting to consolidate, especially in businesses, that is called platform engineering. But what is it, platform engineering? With platform engineer is a practice of extend the control plane of an existing cloud platform to augment its capabilities and in some cases tailor the platform to specific needs of a single use case. In particular, with platform engineer, we can expose high-level interfaces for developer. By doing this, we simplify the approach of developer to Cloud Continuum infrastructure. It's very important the fact that platform engineer works atop of existing infrastructure because thanks of this characteristic, we can exploit existing infrastructure without the burden of creating from the beginning an entire infrastructure with all the complexity also of managing a single site infrastructure. And then we can consider platform engineering for both vertical and horizontal specialization. And in particular, with vertical specialization, we mean the fact that we can exploit platform engineering to tailor a platform for a specific vertical use case. With the term horizontal, instead, we mean that we exploit platform engineering to automate things and to create a high-level interface to manage a complex Cloud Continuum infrastructure that can be used for many use cases. And in particular, one thing that creates the platform engineer, it is that it divides in 3 roles the complexity of creating an application on top of Cloud Continuum. And in particular, as we said, we have product developers that can exploit high-level interface and platform automation to just focus on business logic, on the creation of the business logic. Then we have the platform team that have to expose this type of interfaces to developer and create a platform that actually suits the particular needs of the use case. The platform engineer acts like the platform engineer team acts as a bridge between the developer and the underlying infrastructure. Then we have the usual infrastructure team that have to take care of maintaining a general purpose infrastructure and in particular to maintain the resiliency of the general purpose infrastructure. One of the technology that actually has enabled platform engineering is Kubernetes. We know Kubernetes as an open source system that actually automates automates the deployment and scaling of containerized application. And it's gained a lot of adoption because it has a lot of important features for businesses and for production, like self-healing, scaling, automatic scaling of application, rolling updates, service discovery and load balancing of the different services. And also it has a very interesting approach, which is called declarative configuration, in which we define the desired state of a particular deployment, and the controller of Kubernetes will implement the logic to reach that particular desired state. But let's focus on the Kubernetes control plane, because it's the key point for platform engineering. And in particular, if we explore how actually the Kubernetes control plane is designed with a series of controllers that are called control loops, that are state machine. And what a Kubernetes controller does is actually continuously checking that the desired state permanently saved in his registry and defined by the user is converge with the actual observed state that is of the cluster. And this is very interesting because since 6 years ago, Kubernetes has enabled the definition of what we call custom resources that basically enable us to define any type of custom resources on top of Kubernetes. Then with a custom controller that controls these custom resources, this operator pattern basically enable inside Kubernetes to control any type of external resources, not anymore only container, but as an example, also IoT devices. We can do basically anything with the operator, and this approach is actually used inside the Kubernetes controller to, as an example, manage the states and the volumes that are attached to container. And during the last 6 years, many operator framework has been deployed, as well as there is a lot of documentation that has made very, very simple to create a custom controller and so custom operator on top of Kubernetes. And thanks to this, a lot of services has been evolved in the optics of an operator. And in this slide, we see as an example, an operator that can actually manage, and so it can make what we call an horizontal specialization of our infrastructure, because this operator actually manages the deployment and the configuration of a distributed solution, which is called Prometheus, that enables the pervasive monitoring of our services. Thanks to the Prometheus operator, the user can actually define with an high-level interface what is the desired state of these services. So in practice, what service the Prometheus server have to control, which configuration must be controller, what is the rules to create alerts, what are the dashboards that have to be created, and all of this, while we have to control many different services, and this can be very, very complex, can be done all with a single definition of our resources inside the Prometheus operator. But let's make another case. Let's take the case of Kafka broker. We all know that Kafka is a very powerful broker that enables us to stream terabytes and terabytes of data across the cloud. But one of the problem of Kafka is managing the subdivision of messages among this broker. And this is, it requires a deep knowledge about the Kafka broker and how to actually configure the Kafka broker. This can be, again, all abstracted thanks to a Kubernetes operator that enables to define through high-level interfaces and continuously check that the desired state of our Kafka cluster is always respected. As an example, if one Kafka broker fails for any reason, the Kafka operator will automatically create a new Kafka broker instances inside the cluster and configure the new Kafka instance to recover the original state and the desired state in particular. And all of these have also found a new name, especially in business scenario, that we call internal developer platform. And with internal developer platform, we want to express the need of creating this type of platform that actually simplify completely and try to automate as much as possible by creating what is called golden path, the process of deploying new services or updating existing services, creating a huge increase in productivity and in a speed up of rollout of new services. But this is also been extended a lot by researchers through what we call the vertical specialization and infrastructure specialization. Here you can see some example of paper that actually exploits platform engineer for, as an example, manage critical services in a smart city, or manage through an high-level interface the object of a 5G deployment. And in case of infrastructure specialization, we see as an example the possibility of actually managing a very distributed environment with many sites available in Cloud Continuum and manage all this workload through a single point. And in particular, in the next slide, we will see two simple examples of vertical and horizontal specialization that we recently presented in conferences. In particular, we will start with machine learning cloud continuum operation, or MLCops. MLCops is a framework that we propose that its first aim is to enable the definition of machine learning cloud continuum workloads and manage this machine learning cloud continuum workflow through a hierarchical infrastructure of controller. And in particular, we want to achieve both local and global strategies to optimize the performance of this cloud continuum machine learning workflow. And to do so, MLCops realize two different types of controller. The first controller, it's a local controller that is deployed, as an example, in an edge site and enable to dynamically scale the instances associated with machine learning services, but also changing dynamically the configuration of a machine learning services. While the second type of controller that we can call global controller actually manages the fact that overall the workflow actually meet the expected and the desired performance while exploiting also scale out to cloud infrastructure. And to do so, as I said, we can exploit both dynamic application reconfiguration and local adaptation. And in particular, we considered the use case of anomaly detection workflows, where locally we can achieve through local reconfiguration the dynamic adaptation of the batch size that is processed at each cycle by this workflow algorithm. And as we saw in the first graph, by dynamically changing the batch size, we can achieve with a lower batch size a lower latency, which is better for all this data. But at the same time, as we have to repeat more frequently the re-execution of the workload and of the code, we see also that there is a less tolerance to high frequency and so a high throughput of our algorithm. So we combine these strategies of scaling and of dynamically changing the batch size with global action that actually enable us to offload part of the processing of the workloads to a cloud environment by painting the gap of latency to actually transmit the information to the cloud. And as we saw in the last graph, by combining these two types of orchestration that use both local and global strategies, we can achieve, as an example, a strategy that is called hybrid that can at first increase the number of record processes in each batch, increasing so the throughput of the local edge workflow processing. But at the same time, we can scale to the cloud the workflow services in order to achieve a better latency over time with an increasing number of messages that are submitted to our Cloud Continuum workflow. We will then switch to what we call an horizontal specialization. And in particular, we are part of a project that is called Slices Research Infrastructure. In Slices Research Infrastructure is a European project where we aim to create a large-scale experimental research platform, enabling research all across Europe, but also business to start to experiment with new technologies, and in particular with Cloud Continuum technologies. The Slice RI project and the Slice project is organized in Blueprint, which are sub-projects specialized on particular needs of innovation, of research, such as machine learning or experimentation in Cloud Continuum. And we are actually the maintainer of the Cloud Continuum Blueprint, which is an, let me say, innovative architecture that aims to facilitate the provisioning of distributed experiment among very heterogeneous and distributed resources that are available all across the different universities in Europe. And to do so, the main aim of the Slices Cloud Continuum Blueprint is to create a very resilient to failure infrastructure and to network partition in order to maintain a general high availability of the research infrastructure. And in particular, we can see that the two main objectives of the Cloud Continuum Blueprint is to provide, as we said, a general infrastructure to enable experimenter, a resilient infrastructure to enable experimenter to create their experiment and try new technologies and try what does it mean to actually create an application on Cloud Continuum. But at the same time, the Cloud Continuum Blueprint aims to provide a very simple and reproducible environment for creating Cloud Continuum experiments. And to do so, we want to support the different type of cloud models as well as different type of hardware. The Cloud Continuum Blueprint is organized into two entities: the Slices Federation Central Controller, which is the central entity that actually enables experimenters to define their experiment and so what are their needs in terms of resources to create a Cloud Continuum experiment. At the same time, here is the central point in which Slice Federation Administrator can control the rights and the permission and assign these resources to experimenters. All of this is connected to different Slice sites, which are the physical sites hosted by different universities and research sites that actually provision and provide part of their resources to enable Cloud Continuum experimentation. But again, we said that the objective of the Cloud Continuum Blueprint is to be highly resilient and at the same time to expose a high-level interface to define experiment. So to do so, the Slice Cloud Continuum Blueprint exploit at different layer the concept of platform engineer. And in particular, in what we call the federation plane, which are a series of controllers installed in each site, we enable to create on top of an existing infrastructure the logic of federation by downloading the definition of experiment targeting the site in which the federation plane is installed and configuring the different resources that are requested for each experiment. At the same time, in the federation plane, we have all the logic of synchronization with the Slice Federation Central Controller with the sake of maintaining everything more resilient as possible to partition or failure of one of the sites. At the same time, at a lower level, the Slice Site Control Plane aims to provide a unified interface to define deployment on top of Cloud Continuum resources by providing a very simple and high-level interface that, as an example, we can provide a unique point to define a workload that can span multiple sites. And in particular, the Cloud Continuum Blueprint implementation is an open source project that you can actually download, you can contribute to it, and is based on open source products. It supports the different testing environment, and thanks to a replication based on a checkpoint factor, we can achieve the resiliency of the different Kubernetes sites by creating checkpoints of the different experiment definition and downloading this checkpoint. The creation of that checkpoint makes the definition of experiment immutable for at least a certain time. And since the this definition becomes immutable. This means that can be replicated in as many sites as we want, but at the same time, it means that in a case of a failure, we can maintain the definition of the experiment, and so we can maintain a high availability of our entire infrastructure. So what are the takeaways? What are the key takeaways of platform engineering? So platform engineering can actually enable us to have a modular and very reusable series of tailored containers that enable us to have a vertical or horizontal specialization. When we compare with DevOps, we have the advantages of having an active logic. The controller actually continuously checks the resources that it controls and can implement logic to achieve a failure tolerance or remediation to any type of failure. Thanks to the Kubernetes standard, we achieve a complete integration with DevOps tool, as the objects that are defined in platform engineer are defined in the same language and with the same protocol as standard Kubernetes object. But at the same time, this object enables us to define high-level interface that we can expose to our developer, to our infrastructure maintainer, and so we simplify the approach to Cloud Continuum. What are the cons? First of all, as we said, it's a three-team effort. We need to have the possibility of having one team that can actually specialize to only the business logic, one team that can actually handle and act as a bridge between the developer and the platform, and then we have the classical team that have to maintain the infrastructure. Second big problem, as we said, these controllers are highly specialized. So as an example, if we have created a controller to manage a specific volume or a specific protocol, we need to create another controller if we want to change the technology or the volume type technology that we are controlling. And this creates an initial effort that can be very, very high, because it's true that then we can reuse the controller as many times as we want, and we will have an advantage on the long time. But on the initial effort, we have to create this type of controller. So we are shifting now to a different technology with a completely different approach that in some way overcome some of the limitation of platform engineering. And in particular, serverless computing is a fairly new family of cloud model that completely abstract the infrastructure management, leaving the developer to focus only on the creation of the business logic. So basically, in serverless computing, what we are saying is that we are shifting all the complexity on the cloud provider, leaving the developer only on focusing on the creation of the specific business logic that he needs to create. Some common characteristic of serverless computing is that all the services are characterized by an automated scaling. The services that are hosted inside serverless computing are actually managed. We do not control the creation and the whole life cycle of services in serverless computing. And by making so, all the infrastructure become completely transparent, but also a third very interesting characteristic is that we have a very fine-grained pay-per-use. In classical cloud computing, we are built for the usage of, as an example of a container, is the billing time is the number of hours that the container is actually active on the cloud platform. We are not, if the container is used or not, we are charged in any case. In serverless computing, we have this new type of billing type in which we are charged for invocation for single query for single gigabyte that we are using. Two of the most diffuse model of serverless computing are actually function as a service, in which some user-defined unit of code called function are automatically executed by the platform as to the response of an incoming event, and backend as a service, which are common, let me say, services that we are used to use, that are the classical specialized service that we have known in the past 20 years. As an example, database as a service is an example of backend as a service, or the new ChatGPT as a service is a classical type of backend as a service. So services that we can include in our logic and that are ready to use, again, automatically scaled and managed. So again, this backend as a service has enabled a fast-paced development because it enables to provide ready-to-use services that can cover even complex technology. Again, let me repeat the example of machine learning. In the case of machine learning, we have to create the model, train the model, make the model in production, so run the model in production, make it scale, by the hardware on which that model can run with particular performance. All of this is automatically managed in a backend as a service, and in particular in what we can call AI as a service. And we can have a very different type of backend as a service that we can integrate as ready-to-use services, such as push notification, message-oriented middleware, or analytics. The second type of serverless cloud model is, as we said, the functional service. In functional service, we have ephemeral unit of code that are dynamically run inside an infrastructure. And all of this is completely transparent to the developer. In particular, the developer defines what is called a workflow, and the workflow actually associates a type of an event with the function. Every time the event will be received by the platform will automatically and transparently execute the function on top of the infrastructure. All the infrastructure elements, such as the trigger, the controller, the process that execute the function, are completely managed by the infrastructure provider. And so if we want to create a specialization, if we want to adapt function as a service to a specific use case, you can see that we have to modify the infrastructure itself. So why it's important what can be significant to consider serverless in Cloud Continuum? First of all, as we said, serverless computing completely infrastructure, all the infrastructure complexities. If you are running on cloud, if you are on edge, we don't know. Everything is completely automatized and completely managed by the cloud provider. That we'll have to take care to actually execute the service or the function in the proper site to achieve the desired performance. Also, as we said, one big problem of Cloud Continuum can be that it cannot be convenient. We have to do a huge investment in buy the different site, configure the different site. In this case, if we consider serverless Cloud Continuum, as we said, we have a fine-grained resource utilization in which we will be billed only for the actual utilization, for the actual service that are used on top of the Cloud Continuum. Everything is automatically scaled, and one big difference with platform engineer is that serverless computing, and in particular function as a service, is general purpose. So all this specialization all these performance improvements that are made by the cloud provider are made available for any type of business use case, smart city, industry 5.0, and so on. But there are many open challenges in the terms of Cloud Continuum, serverless Cloud Continuum. And in particular, first of all, we can have, in the case of PaaS, the problem of having what we call multi-cloud backend as a service. Since we are creating very specialized service, one of the big problems that we are facing with backend as a service, but in general with all the type of services, is called vendor lock-in. And with vendor lock-in, we mean that the developer, yes, it's easier for the developer to create an application or a service on top of serverless computing, but often the type of language, the type of API that you have to use to implement that particular service are not standard and are specific of a single cloud provider. This means that if the user wants to opt out or change the cloud provider, you have to recreate many times the service. Also, there are in many cases fee to actually move the services and in particular the data to other cloud providers. A second problem is that, as we said, all this infrastructure is actually managed by the cloud provider itself. So all the performance improvement that are needed to actually achieve the desired performance to meet the requirements of a specific use case, such as in Industry 5.0, a specific latency of the network, have to be done inside the cloud provider. And lastly, the integration of backend as a service and function as a service still is a huge challenge, as we need many times to integrate directly inside the business code of the function, the interaction with the backend as a service, by creating a strong coupling between the two services, but also at the same time by achieving a lower performance. Because as we said, functions are in ephemeral nature, so they can be created and destroyed arbitrarily by the cloud provider to suit the specific SLA, but at the same time to achieve the best cost optimization for the platform. So, as an example, all the technologies that, as an example, use caching or can reuse a connection to, as an example, a database, cannot be used inside a function. And so we can classify the evolution of research in the last 6-10 years on serverless computing on three main directions. The first is to reduce the vendor lock-in by creating an infrastructure in which we can port the function or we can integrate at the same time different backend service. We have a second direction of research that has been very active, which is to improve the performance of function as a service in particular. Why we need to improve the performance of function as a service? Because we want to integrate this type of model in as many scenarios as possible. So we need to face all the problem of performance issue. And finally, in the last 3 years, we are starting to also explore the complexity of managing cloud continuum workflows. So complex workflow may be composed by multiple functions that spans different cloud providers, different models, and different regions. We will make some example, in particular 2 examples of this evolution, and in particular on the front of vendor lock-in and on the front of improved performance. Let's start with the first one. So we said that we have a huge problem in integrating backend as a service inside function as a service. And in particular, the state of the art to do so is to have a workflow integration or a function integration. In the workflow integration, such as the one operated by AWS, the workflow definition, so the workflow we said is the association between a particular event and a particular function. In this approach, we extend the capability of workflow by also integrating the dependency of the function to a particular service, such as a particular database. This approach has a very limited availability, first of all, for vendor lock-in. All solutions of workflow integration are very dependent on the cloud provider that we consider, but also very dependent on the type of services that we want to integrate in our function. As a matter of fact, to integrate a particular function on the workflow and to integrate a particular business services on the workflow, this particular service has to be supported by the workflow definition of the particular cloud provider. The second approach is what we call a function integration. That is the most intuitive one. If we want to integrate and if we want to interact from within a function to a particular database, what we can do? We can directly call the API of the database from within the function code. But this decreases, as we said, the modularity of the function, since if we want to change the database, we have to recreate again the function. And as we said, the function are ephemeral entities. So every time we have again and again to establish the connection to the database, creating a poor performance environment for the function. For this reason, we propose SFIOC, serverless function inversion of control, that exploit dependency injection runtime to dynamically binding a specific backend as a service service inside a function. This is all done at runtime, and it's all done again through high-level interfaces. So we can define a generic database with generic API that the function can interact with to interact with, as an example, the database. This enables us to be cross-platform and multi-vendor. As a matter of fact, SFIOC has been tested on across different cloud providers, but also enable us, since we have the control in some cases of the platform, to provide some infrastructure optimization. And in particular, we can, the architecture of SFIOC is organized on 4 different type of control layer. The first is the SFIOC controller that, as we said, exposes high-level interface and high-level API. And so, again, here we can see, as an example, an approach of platform engineer that enable us to define our workflow as to augment actually the definition of workflow by associating to each workflow a specific service. Then these definitions are stored in what we call the dependency registry, which is the central repository that enable us to store and resolve dynamically the services that are needed by the function at runtime. Then we have the dependency controller that is actually the service that is contacted by the function to resolve a particular dependency and to inject the specific API to interact with that particular service present in the backend as a service. Finally, we have an optional element that can be installed when we have the control of the server infrastructure, which is called a SFIOC injection library. The role of the SFIOC injection library is actually to optimize by dynamically injecting in the runtime of the function the dependency. So it's not a library inside the function that has to resolve the dependency and dynamically injecting in the code, but it is an external element that it's always present, always living, that actually made the injection. And in particular, we implemented the first version of SFIOC to make the resolution of policy, a role-based access control service, and all the SFIOC implementation is available as an open source software, and you can download and test it. But let's see some results. In the first experiment, we saw the difference in performance when we exploit SFIOC with different type of languages across different environments. In particular, we experimented on top of Azure Cloud Function and top of Knative, which is the function as a service platform that is possible to deploy on top of Kubernetes. So an open source and private deployment. And what we can see is that actually compiled languages, and in particular co-function, are the ones that perform best, because again, we are considering a resolution made inside the code of the function. We can see also a huge variation of performance depending on the platform and the language. And this again underlines the capability of provider to transparently provide optimization to end user. As an example, the Azure function can perform better in some cases because automatically Azure store some images of the function inside the memory, and so the execution of the function can be faster. But this also highlights the importance of infrastructure optimization. And so here, as an example, we can see the performance variation when the actual injection is made inside a library of the function, or as we said, the injection is made by an infrastructural element executed by the function as a service platform. And in particular, we compare these two types of injection with a classical injection of services in which we resolve the execution of a service, so the link of, in our case, of role-based access control inside the API gateway, which is the frontier of our typical HTTP request. And as we can see from the graph, the two approach of SFIOC not only can handle a better scalability in terms of request rate by delivering an overall better performance, but we can also highlight the fact that the intervention, the possibility of creating an optimization inside the infrastructure layer can enable us to achieve a better performance that we saw it's very important to enable the adoption of functional service in many different scenarios of Society 5.0. We then move to a different type of optimization, and in particular, we see here a use case in which we want to integrate a function as a service to enable the execution of virtual network function. In particular, in the next years, we saw a progressive softwareization of network function into software-based virtual network function, offering, in this case, an unprecedented flexibility and scalability across a very heterogeneous environment that is nowadays the cloud continuum. The big problem of function as a service is that, as we saw, the ephemerality of the function may also a typical phenomenon which is called cold start, in which, since the function can be not active on the platform when the events arrive, what can happen is that the platform have to recreate entirely the function. This obviously increases a lot the latency, but a second big problem that we are facing with function as a service is that this transparent execution makes it very challenging in edge environment. As a matter of fact, in edge environment, we have a constrained number of resources. So what can happen is that if at the same time two events arrive to our platform, these two functions that have to be executed can compete for resources to execute the two associated functions. And this can actually limit the adoption of functional service in the case of virtual network function execution. For this reason, we propose Tempos for network function virtualization. Tempos for network function virtualization is a custom function as a service platform that, by exploiting different types of acceleration technologies such as TSN, Linux real-time scheduler, or the warm start, can actually enable the differentiation of quality of service of functions that we are executing. The concept here is that it's true that when we are in an edge environment, we can have a conflict for accessing a particular computational resources. But at the same time, it's true that many times the virtual network functions that we are executing are not of the same importance. So if we start to divide this virtual network function by their importance, we can prioritize the execution of some function with respect to the other. And this is a novelty in the case of function as a service, because, as we said, all of this it have to be completely transparent from a developer point of view. And in particular, Tempos for network function virtualization enable the user to associate multiple functions to a single workflow. So in this case, to compose complex workflow by using simple function, and to associate a type of prioritization to each workflow that is executed on top of the infrastructure. On top of this, Tempos runs on top of a message-oriented middleware that enables the federation of multiple sites, so we can consider cloud continuum environment or a multi-edge environment in which the function as a service is run on top of multiple sites, and the role of message-oriented middleware is to make the exchange of the events between the different sites. And as a test scenario to prove the Tempos for NFV capabilities, we create a site-to-site serverless VPN. So basically, we recreate through function the functionalities of a virtual private network in which we compress and encrypt and decrypt the different packets that are intercepted by a specific trigger that can intercept network packets and transmit it to another site. And at the same time, we exploited also the capability of workflow to automatically monitoring the performance of the VPN across site. And as a result, we can see that thanks to the combination of different type of resource prioritization, such as the use of different type of scheduling of the Linux real time, or the use of time-sensitive networking, we can actually differentiate the execution and so the end-to-end latency of the execution of our environment, both when we are in an isolated execution, and as we can see that what we call an high quality, so a strict quality execution of the function, it has not only a less latency of the execution, but also a better jitter. But also in the case of conflict of resources, we can see that the function and the workflow targeted as strict quality can perform better with a lower latency and a better jitter. But especially when we consider the end-to-end scenario, we can also exploit other type of prioritization. And in particular, as we said, the functions are dynamically executed. This means that we cannot predict when a function will actually require a specific some resources on top of our nodes. But one optimization that we can actually do is called warm start. Well, the warm start means that after I reserve an event, I keep the function living for a certain time. This breaks in some way the concept of serverless, in which the function is executed for each event, but at the same time enables us to not pay every time the cost of the creation of the function at the arrival of each event. So in the case of Tempos for NFV, we specialize the strict quality, so the best quality of function, to exploit the warm start, while we are leaving the best effort quality to not use the warm start. In this case, what happens is that the functions that are more requested, that belongs to the strict quality, have some sort of resource reserved to execution. And this is highlighted by the second graph, when we can see how the two workflow that are executed on the same time on our platform, and we are submitting an increasing number of requests to both workflow. We can see that how when we reach a certain threshold, the differentiation enable us to achieve a very good performance for the strict quality, while the best effort quality fastly degrades. So the serverless key takeaways: one big advantage of serverless cloud continuum is that with respect to platform engineer, while it still enables us to abstract the infrastructure to developer and so make the cloud continuum more convenient and more accessible, it's a general purpose model. And this can drastically simplify the execution and management of cloud continuum workflow. Also, the fact that the billing type of serverless computing is fine-grained enables us to achieve a better scale-up of cost when we are trying to adopt the cloud continuum infrastructure. A second big point is that for the first time, we are shifting the control of our application to the cloud provider. This means that the cloud provider can actually implement a new type of optimization that can enable to adopt serverless cloud computing in many other scenarios. Some cons: we are facing an high vendor lock-in with the absence of standards. The integration of other model is very inefficient, and also serverless computing, in particular functional service, is a relatively young set of product and solution that still deserve an evolution. So in conclusion, the evolution of Society 5.0 is demanding the access to new technology, and in particular to new cloud continuum technology in a very convenient way. We saw two possible approach that can enable the access to this new technology through a convenient way by performing new form of optimization, new form of orchestration, and so of automation, but also at the same time by exposing high-level API and high-level interfaces to developer that have not in this way to face the complexity of cloud continuum. As future direction, we will see the adoption of platform engineering and serverless computing in many other society areas that are not yet explored, such as smart cities, smart farming, smart health. The importance of cross-layer optimization is as never as now important. So the capacity of understanding a possible optimization that involve both infrastructural layer, the platform, and the business code. Also, we are seeking, we need actually the promulgation and adoption of many open standards that can enable us to reduce the modularity, increase the adoption of this sort of tools, but at the same time facilitate the development of new technologies. And with this, I've concluded. If there are any questions, I would be more than happy to answer.
So thank you very much, Andrea, for your presentation. This topic has been discussed in other keynotes here. So it really is very important for our INCT. So we have already some questions in the chat. So the first one is from Eduardo, and he says, "Many thanks for your talk. Could you please give us more information on what we need to do to run our experiments using Slice? So if someone wants to use it, so what is required to do?"
The Slices AI infrastructure is a long-term project. If I'm not wrong, it would be a 20-year project that we are developing in European Union. Actually, there is the Slices basic infrastructure that is already available and enable you to run on top of container and virtual machine and physical nodes your workloads. If you want to execute the Slices Cloud Continuum Blueprint that I have presented in this slide, you can execute it locally on top of your cloud. There are many automation tools that we are actually releasing, and there is a new release that we are committing in this day that also enable the support to Ansible and the targeting of generic virtual machine, generic Proxmox environment, or generic physical nodes. So in general, you can have many possibilities. You can exploit the Slices basic infrastructure to host simple workloads. If you want to automate the provision of a multi-cluster environment in which you want to create cloud continuum workloads, you can have a look to our repository that is the Slices Cloud Continuum Blueprint. It's open source. You can download it. You can test it locally. You can test it on the Slices basic infrastructure. Very soon will be available an automated way to actually make tests of Cloud Continuum on the Slices basic infrastructure through the Slices Cloud Continuum Blueprint. And you can actually test on your own clouds, like if you have a Proxmox or a stack on your university, you can have a reproducible way to create your experiment.
So you, I cannot hear you. I cannot hear you.
You didn't hear me?
Now again. Okay. So you said that Slice is a 20-year project.
Mm-hmm.
So when has it started, and up to when it's going to last? So because my question is like, I'm not used to projects that last for like 20 years, and I wasn't aware that the European Commission was funding projects for such a long time.
Since after the COVID, we have a first round of funding, and we are actually seeking for new funding for the slices array. Actually, the slices research infrastructure, it's a consortium. So it's maintained by 16 university and research center, and so in this case, for this reason, we consider it a long-term project that is not bounded to single round of funding of the European Union, and has been started 2 days after COVID. So I think it is 3 years, 4 years that this has been started.
Okay. Okay, it makes sense. So thank you. Another question from Alexandre. Using different infrastructure providers, public and private clouds, and edge infrastructure, and of course, doing so continuously is a very complex task. Are there any pilots at this level of complexity being performed in smart cities use case? In particular, using edge infrastructure seamlessly?
Yeah, there are many articles that already explore the challenge of integrating edge computing and cloud computing in the smart city, especially for what we are calling now digital twin. Actually, in my city, my small town, we are in what is called the digital twin of Bologna, which is one of the platforms that actually have to integrate different type of cloud in our use case. So in particular, we are integrating an HPC infrastructure and a standard private cloud. And I don't know if there are actually pilots that you can access for smart cities because of the big problem of data regulation and data access. I know for sure that there are many platforms, many open source data that you can actually already download from many municipalities. I know that as an example, in Europe, there are different sources for the data that you can actually exploit for your experiment. As an example, the European Commission has an open data portal. Each state in the European Union, I think, has at least Italy, I'm sure that has a data portal. And also many times there are cities that expose open data that you can exploit in your setup. Then having access to real test use case scenario is one of the objectives actually of the Cloud Continuum blueprint. As a matter of fact, by creating this type of distributed environment, what we are seeking also to integrate is sensor, new type of technology, network acceleration, 5G networks, and so on, and also sensor from the smart city. So one of the objectives of the slices research infrastructure is, as a matter of fact, to enable this type of experiment. But as of now, I don't think that there are many. There is Cloud Lab that you can actually exploit, that I know, that enables you to define a deployment, and that can have many IoT devices and other type of nodes. And this is an example of Cloud Continuum environment that you can experiment with for smart city.
Okay, thank you. And I have like a question of a subject that is currently everyone talks about it, like it's about AI and AI agents particularly, because you mentioned that when you do this platform engineering and you create like this specific platform, you need these controllers. And as I understand, they need to be like tailor-made for that specific applications. Could you use, or are you considering to use like AI agents? That's what you do is to tailor just a prompt, and then the AI agents or LLMs or whatever, they behave as controllers, so that to avoid being to having to develop like a new controller whenever you need like a new platform.
This is my experience and my experience by now. And I experience especially with GPT-5. Maybe the next model would be much more powerful. I'm sure that they will be much more powerful. But what we are seeing now, also in big cloud provider, is that this type of agent and the LLM in general are used to create even an higher level interfaces. So in general, what you have, as an example in AWS, is that you have an MCP server or in general an LLM agent that can actually, you can type your request, your infrastructure, and then it translates into Kubernetes configuration, Terraform configuration, Ansible infrastructure as code configuration in general. Why, in my opinion, we cannot still exploit AI agent as orchestrator is that because they are not predictable. We don't know two reasons actually. The first is that they are not predictable. I don't know if there is these things that is called randomness or the things that make the creativity of LLM that they makes them very not deterministic. So what in contrary, in orchestration, what we want to have, it's a very deterministic process. I want to have a pod, I want to have it start now. If the LLM agent for this type of non-deterministic behavior I cannot know what will be the end result. And the second problem that actually I see is that LLM are very, very good for very simple and yet explored situation. Here in Cloud Continuum, we are facing an unprecedented complexity. It's very hard that an LLM can actually map the SLA or in general the contract or the specific that you have for an application on a very complex and heterogeneous infrastructure. This is at least is my opinion.
Okay, yeah, it makes sense because some probabilistic behavior would really bad, but an hallucination
exactly.
is not desirable for sure. So, Andrea, thank you very much for being here with us. It was a pleasure having you here, and I hope we can meet in person soon, and I hope you keep like contributing with this project, and you leave your I'm seeing that your email is there, so there are many researchers from our project that are working on similar topics. Maybe they can contact you if to start some collaborations or just to ask some questions.
Yeah, it would be a pleasure. If anyone wants to contact me, they are more than welcome. Also for collaboration or question.
Okay, thank you very much again. So with this, we'll end our transmission. We'll end our streaming right now, and we hope to see like our followers and the audience in our next seminars in the future. There is one program for here in 2 weeks, the 27th of November. So as they say, stay tuned. Okay, thank you very much, and the transmission will be ended right now.